Hi, my name is Jennifer Brana, and I'm going to talk about how to design a coherence protocol that Brana, and I'm going to talk about how to design a coherence protocol that simplifies the system integration of cache-attached accelerators. Conventional systems only process data on cores, which forces data to traverse the full memory hierarchy before it can be processed. Cache-attached accelerators have been proposed as an alternative to the traditional processor-centric design. Accelerators are placed within the cache hierarchy, allowing the processor to offload computations closer to where data lives, significantly reducing data movement. In addition to reducing data movement, cache-attached accelerators benefit from using the shared memory space. This allows for simple and fast fine-grained communication, making the accelerator easier to use. However, to fully benefit from sharing the address space with the processor, the accelerator must maintain coherence with the rest of the system. Often, maintaining coherence can increase overhead state, require significant verification effort, and degrade the performance of the baseline processor. Kobold is a new coherence protocol designed specifically to avoid these complexities to ensure simple integration of cache-attached accelerators. For concreteness, we focus this talk on a recent system called Taco, which utilizes cache-attached accelerators. Each tile in a coherent multi-core is augmented with an engine, giving the engine efficient access to data in the tile's caches. Each engine also contains its own private, cache-coherent data cache, the EL1D. Kobold's goal is to efficiently keep the EL1D coherent with the rest of the system. A naive system treats the EL1D as an additional share into the LLC, but this doubles directory state, and even worse, it causes excessive coherence latency. In chip multiprocessors, the last level cache banks are often far from the tile, so sending requests through the LLC is quite wasteful when engine and core reside on the same tile. Kobold fixes this problem by attaching the EL1D to the L2 cache, thus reducing communication to the LLC. Now, when the core requests data its local engine holds, Kobold Coherence Protocol handles the request within the tile. As we can see from the perspective of the full chip multiprocessor, costly accesses to the LLC are now avoided. Let's see how Kobold achieves this. Kobold is a new type of hierarchical coherence. Unlike traditional protocols, the L2 is not inclusive of the EL1D for performance benefits that I will discuss later. And furthermore, the EL1D and L2 operate as peers via snooping to handle many coherence requests. We implement this by adding an additional directory structure, the misdirection filter, within the L2 cache to track coherence between engine and core. Kobold has two main performance optimizations for cache-attached accelerators. To avoid polluting the L2 cache, Kobold makes the L2 cache non-inclusive of the EL1D, so data is only stored in the L2 when the core requests it. To minimize latency on EL1D misses, Kobold can send speculative requests from the EL1D directly to the LLC. These optimizations are explained further in the paper. Finally, Kobold's coherence modifications require verification. Adding features to a coherence protocol can significantly increase verification complexity. In Kobold, we hide the details of the engine cache from the LLC so that the L2 and EL1D appear as one unified cache to the LLC. This allows the LLC protocol to remain the same, reducing the verification necessary for the system. Our preliminary results are very encouraging. We verified the stable state protocols using the Murphy model checker. We used Cacti to evaluate the error requirements of Kobold's MDF. Compared to the existing caches, the MDF adds an area overhead of only 0.09%. Thank you, and please see the full paper in Cal to learn more about Kobold.